Hello everyone. I am Sara Sartoli. I work with Dr. Akbar Namin from Texas Tech University. Now I'm going to present a semantic model for action-based adaptive security. My talk is organized as follows. I start with presenting the motivation of the work. Then I continue with giving a brief background and introduce the research problem and contributions. Then I'll explain why we have used answer set programming as underlying logic. After that, I present a running example through which I'll explain the proposed security requirements model and topological model. Then I continue with presenting analysis stage and planning stage in the adaptation process. Finally, I present the results of the case studies and conclude the talk. Here is one motivation example. Consider a hospital in which surgical device vendors need to be present in the operating room when a new surgical device is being used. Let's assume the hospital policies don't allow vendors to be unaccompanied in the operating room. In this hospital, Nancy and Nicole are nurses, and Valerie is a vendor who has to be accompanied in the operating room. Now let's consider Nicole is preparing the operating room before a surgical operation. Valerie arrives and she wants to enter the room. Nancy, another nurse, escorts her to the operating room. After a while, Nancy leaves because she assumes that Nicole stays in the room. Nicole also receives an emergency call. She leaves the operating room in a situation where the security requirement is violated. As you can observe, a sequence of permitted actions can cause a violation, and this motivates the need for runtime system and environment models that support adaptive security. Let's look at another motivation example. In the hypothetical hospital, authorized employees are allowed to use their own device for accessing and storing patients' health information. The policies of the hospital says that only authorized personnel are allowed to store patients' health information on their device. Assume Nicole is assigned as Pamela's primary nurse. Therefore, she is allowed to access and store her information on her device. She is also allowed to use the HIPAA-compliant file transfer systems and transfer the data on her device to the other employees. Nicole transfers Pamela's data to Nancy. Nancy is not Pamela's primary nurse. Thus, she is not allowed to have Pamela's health data on her device. Therefore, Nicole's action leaves the system in a violation state. This illustrates another example where a sequence of permitted actions caused a violation. In our paper, we presented a semantic model for topology-aware adaptive security. Adaptive security aims at enabling software systems to adjust their protection mechanism and continue satisfying their security requirements in the changing operating environments. Topology is one of highly dynamic aspects of the operating environment. By topology, we mean a representation of physical and digital elements and their structural relationship, such as containment and communication relationships. We want to perform runtime verification and determine action plans. This problem is challenging. Appropriate formalisms are needed to represent topology and track its changes at runtime. Ambient calculus-based dynamic topological model has been used to support adaptive security. We want to present a more comprehensive semantic model capable of representing topology along with security requirements and system execution model. This semantic model allows us to determine action plans and do runtime verification. We adopt feedback loop as reference model. Runtime verification requires monitoring operating environment, Maintaining knowledge about requirements, environment, and system execution, detecting possible violations proactively, and finally determining action plans to mitigate possible violations. These steps form the contributions of our paper. We present an ASP-based semantic model. Our semantic model has three parts: a security requirements model, an environment model which describes the topological structure, and a system model which describes the evolution of topology in response to agent actions. Then we reduce analysis and planning activities to finding answer sets of ASP programs. The question to be answered is why ASP? ASP is a non-monotonic declarative language. Being non-monotonic makes it suitable for reasoning in dynamic environments with a high level of uncertainty. Basic ASP rules are as follows. This rule can be read as at least one of A's is believed if B's are believed, whereas C's are not believed. NOT symbol is called negation as failure. Unlike classical logic, NOTC doesn't mean that C is believed to be false. Instead, it means that there is no reason to believe in C yet, and this allows us to explicitly represent incomplete and uncertain knowledge. Now I'm going to talk about a running example. Using this example, I'll illustrate the proposed semantic model. This is the floor plan of our hypothetical hospital. The red parts are clinical areas and are protected by secure doors. The right parts are public areas. Wi-Fi internet is provided in the clinical area. Employees are allowed to bring and use their own device to access patients' information. Employees can store encrypted data on their device, and they can also transmit data to other authorized employees using a HIPAA-compliant file transfer platform. Let's consider that the following security requirements are implemented in the hospital. According to Security Requirement 1, unless accompanied by a nurse, vendors are not allowed to be present in the operating room. Security Requirement 2 says that no more than one significant other may accompany adult patients in the procedural treatment unit. According to Security Requirement 3, patients' health information might only be transmitted to authorized personnel who are allowed to access the information. All the security requirements can be described in terms of the structure of a part of hospital. We represent the structure of topology using a containment hierarchy and a communication graph. Containment hierarchy abstracts four types of relationship. One of them is being enclosed. For example, Nicole is in the operating room. Another one is possession. For instance, Nicole has a device. Another one is accessibility. For instance, operating room is accessible from reception area. And finally, the last one is storage. Like Pamela's health data is stored on Nicole's device. These relationships are expressed as containment hierarchy using contains predicate. In communication graph, we describe which device is connected to an access point or another device which is acting as an access point. We use connected predicate to describe communication graph. For example, Nicole and Nancy's devices are connected to the wireless access point. We represent the transition of the system as evolution of topologies. In this transition diagram, each state represents a topological structure, and each transition corresponds to an action exercised by an agent. We represent the transition function using three types of ASP rules. The first type represents the direct effect of actions on the topology. For example, this ASP rule represents how location of an agent changes when inter-room action is exercised by the agent. In addition to direct effect, we need to express indirect effect of actions. Indirect effect of actions put constraints on the states of the system. For example, according to this ASP rule, an agent cannot be located in two locations called location 1 and location 2 simultaneously. We also express inertial law using capabilities of ASP to represent defaults. According to inertial law, topologies remain as they are unless some actions are exercised by agents that change the structure of topology. These two rules represent the ASP counterpart of inertial law. So far, we have represented the structure and evolution of topology. In order to perform runtime verification, we need to have a model of security requirements as well. We represent the violation to each security requirement as description of a part of topological structure. For instance, security requirement 1 can be described as a scene where Valerie is inside the operating room while no nurse is in the operating room. According to security requirement 2, only one significant other may accompany adult patients in the procedural treatment unit. The violation to this security requirement can be described as a scene where an adult patient has more than one visitor in the procedural treatment unit. Our final goal is to prevent actions that leave system in such violation states. Violation of security requirement 2 can be represented as this ASP rule. And finally, let's represent security requirement 3. This requirement states that patient health information might only be transmitted to authorized personnel who are allowed to access the information. The violation of this security requirement can be described as a topological structure where some data is stored in some device, and the device belongs to an unauthorized employee. Using the proposed models, I'm going to describe analysis activity of adaptation process. The input of analysis activity is the topological model and security requirements model, and the output includes all possible execution paths on which some security requirement is violated. The main idea is to build an ASP program whose answer sets correspond to all possible violation scenarios. We build such a program by encoding topological model, security requirement, and one domain-independent action-generated module, in which we generate actions up to k steps. Planning stage uses the output of analysis stage. Then it determines action plans to enact an adjustment to each possible violation scenario. We represent planning activity using a domain-independent ASP-based module. The first rule revokes permission to an action if the occurrence of the action causes a violation state in the next time step. The second rule suggests a corrective action if the occurrence of the action changes the system from a violation state to a safe one. To evaluate the feasibility of our models, we answered this question. What are the action plans generated for each of two examples illustrated as motivation? We represented initial structure and evolution of topology and security requirements. Then we let analysis and planning activities look 2 time steps ahead. And finally, we reported action plans generated by the proposed reasoning scheme. For case 1, when the vendor was left unaccompanied in the operating room, 94 answer sets are generated. In 38 cases, planning stage suggests that vendor needs to leave operating room. In 28 cases, planning stage suggests that Nancy, a nurse, enters operating room to resolve the violation. And in another 28 cases, planning stage suggests that Nicole, another nurse, enters operating room. For case 2, 24 answer sets are generated. In all cases, planning stage suggests prohibiting transferring data from Nicole's device to Nancy's device. To conclude, an ASP-based topological model, system model, and security requirements model are represented. Then analysis and planning activities of adaptation loops are reduced to finding answer sets of ASP programs. A case study was represented to demonstrate the feasibility of our approach. In future, we plan to extend our work by generating potential insider threats and determining action plans to prevent them. Thank you for listening to my talk. We'd love to hear your invaluable feedbacks and answer your questions through email.